No, I found it. He gave me finger guns, and then I gave him finger guns.
Okay, get started. Could you all contact me? Good afternoon, everyone, and welcome to the University of San Francisco's MSDS Data Science. My name is Sean Butcher, and I'm the Marshall Data Institute. And I will sorry about that. This seminar series is produced by the University of San Francisco's Master in Data Science program and sponsored by USS Data Institute. If you're interested in learning more about the Data Institute or supporting the Data Institute, you can reach us by email at datainstitute@usfca.edu, on the web at usfca.edu/data-institute. I also wanted to bring your attention to some certificate programs that have been running this spring by the Data Institute. We're running a certificates on Introduction to Data Ethics, Introduction to Machine Learning, SQL for Data Analysis, and Applied Machine Learning. If you want more information about how to sign up for these certificates, you can visit us on the web at usfca.edu/DICERTS. Today, I'm pleased to welcome Erin Ledell, who is the Chief Machine Learning Scientist at H2O.ai. Erin's talk today will cover Admissible Machine Learning. If you have questions during the seminar, during the presentation, please, if you're attending online, enter them in the Q&A box, which you'll see either at the bottom or the top of your screen. Or if you're here in person, please raise your hand and I will hand you a microphone. With that said, thank you, Erin.
Thanks. I will try to share my screen now. And let me know if it looks good. Can you see my slides okay?
Yes, we can.
Okay, great. All right, so I'm sorry I couldn't be there in person. I decided it would be a little easier to give a talk without wearing a mask. So I thought I would do it from home. So I appreciate those that did show up, and then thanks for everybody else for showing up online. So today I'm gonna present a new topic in machine learning called Admissible Machine Learning. This is my first time presenting it, and it's new, so you might have a lot of questions, and feel free to ask me questions during the presentation if you want to put them in the chat. It might work better if we do kind of like short questions, clarifications during the talk, and then maybe longer, more discussion questions at the end. I don't know how long the talk will be yet, because as I mentioned, it's the first time presenting it, so we'll see how it goes. But I will try to stay on track and yeah, keep us going. So as Sean mentioned, I'm the Chief Machine Learning Scientist at a company called H2O, which is in the Bay Area. We're also, see, I hear some feedback. Yeah, I'll just wait a second to make sure that's okay. Yeah, so let me just move on. So this is the agenda of what I'm going to talk about today. So we will talk a little bit just about what is interpretability and fairness in machine learning. That's sort of the general umbrella under which this topic falls. Then I'm going to introduce admissible machine learning and a technique or graphical tool called the Infogram. And then I'll show you how we implemented this in H2O and basically teach you how to use it in R and Python. It's pretty straightforward and it's already in H2O, so you can use it today if you like. And then I'm going to just give some examples, so some real life data examples of how to use this. And then I'll also kind of briefly introduce a concept that I will call Admissible AutoML. AutoML is kind of my day job, let's say. This is what I've been working on since around late 2016, 2017. So I will show you how that integrates as well. So first, what is interpretability and fairness in ML? I know that USF has a pretty strong reputation of talking about topics like ethics in ML and fairness and bias. So you probably know a bit about this already, but let me just, at a very high level, introduce some of the concepts. So the term interpretable in machine learning refers to techniques or models which can be understood by humans, essentially. And then, of course, some models are inherently interpretable. Probably the most recognizable two are linear models and decision trees. There's a few others like GAMs and things like that that would be considered interpretable. But if you really want, I mean, the human brain compared to like a computer is pretty simplistic in terms of what it can understand and wrap our heads around. So linear models are straightforward, so are decision trees. So if you want something interpretable, it's most likely going to be something like that. And then I'll also just mention that there's also the term explainable ML, and I want to just mention this because this is different. So explainable ML typically refers to explaining black box models, which are not interpretable. So let's say like a GBM or deep learning or something like that. So interpretable means let's really try to make it so that a human could make sense of it, and not just like a machine learning human, but like any human. And explainable really has, the goal is very different, I think. I mean, the goal is the same, is to increase understanding, but explainable refers largely to explaining black box models. So, so just to make this a little bit more precise, so there's this book that I think is really great by Christoph Molnar. It's an online free book, you might have seen it, called Interpretable Machine Learning. And he has a good definition. It's actually from, you can see the reference below, it's from a paper called Definitions, Methods, and Applications in Interpretable Machine Learning from 2019. So I like this definition a lot. So interpretable machine learning is a useful umbrella term that captures the extraction of relevant knowledge from a machine learning model concerning relationships either contained in data or learned by the model. So that's just maybe a little bit more formal way of saying it. So it's not exclusively models, it's not exclusively data, it could be both. And today we are gonna talk about really more data, but it's also stuff learned by the model. So a similar type of concept that you might be familiar with, or a popular tool that you might be familiar with, is something called partial dependence plots. So this is something that I would call an interpretability tool. So, and it it is something that you learn from the data, and it's probably one of the most simple, straightforward interpretability tools, and that's why I like it a lot. It basically just shows you how does the response or the outcome vary over, like if you vary one of the variables. In this particular example, if we changed income, from 0 to a high number, then we can see how the response, and I can't remember actually what this example is from, but let's say you're predicting something where income is a variable. Maybe you're predicting whether or not somebody is credit worthy or something like that. So yeah, so these are useful tools. They're used. This tool is over 20 years old, but it's still one of the best in my opinion. Okay, so that's interpretability, sort of broadly, very, very short, high-level overview. So let's now talk about fairness. So these are different things, interpretability and fairness. I would say interpretability is maybe sort of a prerequisite for fairness in a way, or it's sort of, they are kind of related. So in order to evaluate fairness in a model, you need tools to do that, and sometimes those are interpretability tools. So what is fairness in machine learning? This is kind of a hard question to answer because it's sort of a loaded term, first of all, and then it also sort of describes a whole bunch of different problems, and it's not a specific approach. And there is no real definition of like, what is a fair model, because the term in itself is sort of just unprecise. So I will try to define it a little bit more on the next slide. But so one of the reasons why this is sort of hard to evaluate in machine learning is because there's these different concepts of fairness that we have to think about. So first of all, I'll just preface this by saying, like, this typically applies when you have data sets that involve people and demographic data. So if you're evaluating whether, like, a very common example is like predicting whether or not to give somebody credit, if you're a lender or something like that. And I'll use a couple of examples throughout the presentation that have to do with that. But basically, fairness is hard because there's individual fairness. So the fairness for an individual to get, like, like where everybody can sort of have the same opportunities. And then there's group fairness, where, like, sometimes if you increase fairness for one group, it reduces fairness for another group. So it's kind of this hard thing to wrangle. And then there's also, like, law. So sometimes fairness is actually encoded into certain laws, like, and so that's obviously also a moving target, and it's also dependent on where you live. So there's all sorts of, like, slippery concepts that are hard to wrap our head around in terms of fairness in ML. But let's maybe try a little bit harder. So I would say, like, fairness in ML refers to techniques for measuring and or mitigating the disparate impact on subsets of people, which are defined by protected attributes. So that word can mean different things, but generally something like age, gender, race, those attributes are protected under certain laws in certain countries. I'll talk about that more in a minute. But also, when we talk about these things, there's often, like, different meanings of the word. So disparate impact or adverse impact, those both have sort of colloquial meanings, but also legal interpretations under certain circumstances. So when we do talk about these things, it's important to be clear about what we mean, and are we talking about the legal definition or just a general definition, etc. So you can start to see why some of this stuff is challenging. So just some of the basic methods that people use to diagnose bias in models. So there's probably the most popular thing that people know about is something called the adverse impact ratio. It's also sometimes called the 4/5 rule. WikiHow.com has a great explanation for things. Actually, WikiHow in general has pretty much an explanation for anything with like wonderful visualizations. So if you enjoy learning in that way, in a visual way, it's a good website. And so, yeah, I just got this image from WikiHow, but it's essentially, it's just a way to like, it's let me rephrase it. So in terms of US legal theory, for example, the term disparate impact means a practice is considered illegal discrimination if it has a disproportionately adverse effect on members of a protected group. And the way that you do this is you calculate something called the adverse impact ratio. There are different metrics for either classification or regression that people use. So there's a whole bunch of different fairness metrics. I think there's, I don't know, certain packages in R Python that have like hundreds of fairness metrics. And I don't think it's useful to have so many. I don't think we need hundreds of them, but maybe we just need better ones. But I'm not gonna spend too much time on defining these different terms, but you can look them up and learn more about them. Really, this is just meant to sort of introduce some of the concepts. So this is another resource that I would recommend. So the fairmlbook.org. It's a book that's a work in progress. I think it's been in progress for over a year, maybe 2 years at this point, but a lot of the chapters are done and there's a lot of good data in it. So these are some quotes from this book. So the term bias, in order to kind of define this a little bit, it can refer to demographic disparities and algorithmic systems that are sort of objectionable for societal reasons, because there is also like a statistical definition of bias. What we're talking about here is when a model treats certain subsets of demographic groups differently and in kind of an unfair context. And usually there's also some greater context, it's just sometimes the differences maybe aren't meaningful, but sometimes they can have a huge impact on whether or not you get credit or can buy a home or things like that. And those have huge impacts and can further punish usually people that are already marginalized in some way. And so I would say a goal of fair machine learning is identifying and reducing these biases, but just again, this word is tricky. This doesn't guarantee that a model is fair just because you've met some metric of like the adverse impact ratio is, less than or greater than a certain number. So be careful when you sort of wade into this world of not trying to slap like a, fairness stamp on something. I think that's a very tricky thing to do. And even, when we're developing software and we're naming things, like, I think it's a little, dangerous to say like, this model's fair, yes or no, or things like that. So also as you, go further in your career and maybe you're developing some of these methods in the future, just keep that in mind because people will rely on your tools. And generally what I've seen is people like easy answers. So if you added a column that said fair or not fair in your software, people would trust that and then use that and bring that to their boss and say, hey, we've trained a fair model because this software says so. So just make sure to not do that. And I've tried to do that in my own work. So a couple just points on like, how do we actually remove bias if it's there? Because we all know that there are many historical biases in data. And I've given whole talks about that before. And if you're, interested in that, I do have some other talks about it, but we should just assume that this is true. There is bias in data. It's causes all sorts of problems if you're not addressing it. So there's different ways of addressing it. You might get lucky. You might train a model and you evaluate based on some fairness metrics, and it might be okay. But if if you have demographic data in there, it might not be okay and probably won't. So you do want to take a look and try to fix it if you can. And fix is also maybe not the right word. Maybe reduce is a better word. So try to reduce the unfairness. Sometimes we can't eliminate it altogether. So there's kind of three main approaches. So one, you can kind of fix the data. You could fix the model, or you can fix the predictions. So again, I'm not going to go deep into each one of these different methods or list all the methods of how to do each one of these. But what the approach that I'm going to talk about today is really geared towards fixing the model. So and I would say it is an attempt to sort of regularize the impact of the demographic features, or basically just remove hidden features that are sneaking this bias into your model, and you might not be aware of it. So that's what we're going to talk about. All right, so admissible machine learning. So what is this new thing? Well, first I'm going to talk just sort of broadly about the goals and the features. So there's this term that people use called fairness through unawareness. So this is kind of the idea that you have some demographic data columns in your data, and if you just remove them, then how could it be unfair? Because the model never saw those columns anyway. So this is, I mean, I think anybody that's been working in this field for more than, I don't know, a few months should be aware that this is not a real thing. So you can't get fairness just by removing the age column or the race column from your data. There's quite often many correlated variables. I mean, the most, canonical example of this is zip code. So let's say you removed race from your data set, but you kept zip code in there. Well, zip code is basically a proxy for socioeconomic status or race. It's very loaded. It's loaded with bias. So you think, what is a number, just a zip code, have anything to do with it? Well, you just have to peel back the layers. Some of them, like zip code, make sense when you think about it a little bit, but some of them are more sneaky, and they're things that you would never think could leak bias into your model. So this is kind of what we're trying to address here. So one approach is to kind of just think really hard about the data that you're putting into the model and think about, do I think that could be possibly correlated with, race or age or marital status or things like that. But that's kind of, well, number one, it's not like it's not an approach that can be repeated in kind of a principled manner. It's kind of a messy way to do it. It's better than doing nothing. But what we would really like is some kind of technique that is going to work every time and is going to systematically address the issue rather than relying on domain knowledge and stuff like that. So one of the goals is to sort of address this fairness through unawareness thing. This isn't unique to Admissible ML. This is kind of a goal, I would say, of all of these other types of tools. So then one of the features of Admissible ML is it filters out redundant and unsafe variables. So it's actually trying to address more than just the problem of fairness. Sorry, I was just reading the chat. It says somebody's mic is hot and he is talking as you're presenting. So I don't know if that's if somebody could address that, but I can't hear anything, so I'm not sure. But anyway, so Admissible ML, it not only addresses the fairness issue, it's also just trying to create better models that are not using a whole bunch of redundant variables. So I am a little bit focusing on the fairness in this case, because I think that's one of the, it's almost more valuable than the other part, but it's really just to get rid of all the unnecessary and harmful features in your data. And then another goal of this particular effort was really to tackle the bias head on. So there's different ways of doing this. Like I mentioned, like you can do it after the fact. You can take a model and try to debias it after the fact. Or you can just try to do a very exhaustive search until you find a fair model. But those approaches are, it would be better if we could just address it from the beginning and build fair models to begin with, rather than spending the time or computation power to do it the opposite way. So that was one of the goals as well. And then the other goal really is like, can we build something that's easy to use so that everybody can just use it? And then there's no complaining about, oh, I don't know how to do fair ML, or like, it's too hard or it's too sophisticated. Like, let's just make it really easy so that people can just do it. And one of the motivations for me was I've been building AutoML tools for the last like 5 years, and I've personally, contributed to making it very easy to do machine learning, which, at face value, that sounds great. We're promoting access, to doing hard things that used to take a lot of sophistication to do, and now it's super easy. But as I've mentioned in other talks before, this has also led to sort of inexperienced people, or maybe just even not even people, but like people writing a program to like automatically train models and not look at them. It's also made it really easy to do a lot of machine learning and to create a lot more problems with machine learning. So my goal here is to also create some automated way of making it safe, because we've sort of let put the toothpaste is out of the tube or something. We can't put it back in. So now we just have to like put guardrails on this stuff. Okay, so, all right. So what is this? It's a paper. So it's new research. It was just published last month. We have been working on it for a while. So it's a paper written by a researcher who is a consultant at H2O. And, my role in it was sort of advising and managing and figuring out how to make this paper into software. So yeah, it's you can read the whole paper. It's actually a very good paper. It has a lot of information in it. I will try to present like tiny bits of it. But if you really want to know the theory, I recommend the paper. If you don't want to know the theory, then I would recommend the user guide, because I sort of distill everything into, something that you don't need to know the theory. So this is now available in H2O. And really what it is it's a suite of algorithmic risk assessment tools. And the screenshot that I have here is it was published in the journal Machine Learning, but the article is not, at least at this point, open access, unfortunately. So I would recommend the archive link. And I would try to get it to be open access, but it unfortunately was not. Okay, so where did this idea come from? So about 1.5 years ago, I gave a keynote at the Use R conference in 2020. So, and it was sort of all about like, what can we do about this, this thing where we've created all these AutoML tools. Now it's really easy to use. How can we be more responsible about that? And so this is kind of like my first attempt, let's say, into this space of like, how do we put guardrails on easy to use AutoML? And I would say like my first attempt was sort of a failure. It was like, okay, what if we just, generate all these fairness metrics and we train a whole bunch of models using H2O AutoML, and then we evaluate each of the models on their fairness. And then like, probably since we've, generated so many models, some of them will just randomly sort of be fair because all the models are very different and have different properties. And so like, let's see what we can do with that. And so what I did was sort of build a little extension. It's not, this never actually made it into H2O, as kind of a prototype. So what I would do is like add a column to the leaderboard for AutoML. So when you train an AutoML run in H2O, one of the things that you get back is sort of this data frame that we call the leaderboard with all the models, and they're ranked by performance metrics. So what if we added like adverse impact ratio to the performance metrics, and then we can sort and figure out like which ones are okay. So then I did that. This is on this data set, which I'll introduce a little bit more later, but it's called the HMDA, the Home Mortgage Disclosure Act data set. It's about home lending or loans for homes. And so, you know, I calculated all the adverse impact, and like every single model was having an adverse impact, meaning every single model was discriminating against certain subsets of people. And you'll see in the you probably can't see the slides that much. I have a link at the bottom where you can see the original deck, but basically, like, you know, every model was discriminating. And you know, I didn't do anything to the data to try to make it not discriminate. I just thought, you know, maybe there's some exhaustive approach to this. So that, I would say, you know, didn't work. Okay, so what can we do from there? So then, you know, we had a talk with the researcher, and this is basically what he came up with and wrote a paper about. So, all right, so the next like 3 slides are going to be the most dense of the whole thing, and you can, you know, glaze over if you'd like or not, but I just put a few things in here from the paper just to address some of the theoretical stuff, because it is sort of the first time anybody's hearing about this, so I thought I would at least try to explain some of it.
Hi, Erin, we do have a question from the audience.
Yeah, oh, it says some models will be fair, similar to Rudin's, that some will be interpretable. I'm not super familiar with that, but I think, I mean, I know about Cynthia Rudin, but I think, yeah, it might be a similar kind of concept. Like if you iterate enough, like some of them will just, you know, because we're doing sort of a random search, perhaps some of them will randomly be fair. I think that might be similar to what you're saying, that some of them will be, yeah, I'm not sure about that. I'll have to look that up after.
We also have a question from someone here in the audience.
Sure. Mm-hmm.
So I wanted to ask, so what metric do you use to evaluate the fairness of a model? And how do you make sure that every kind of bias is removed from it?
Okay, so, well, I will talk more about some of this at the end. So what I want to emphasize is like, this is a method for visualizing and evaluating risk. And then it's sort of a separate task then afterwards to then use all these other metrics that I've mentioned, like adverse impact ratio, et cetera. Like there is really in the fairness world, like no, you know, single method that says if you meet all these like metrics, then your model is fair. There's a lot of like disagreement about what fair means and how to evaluate it. So I think everything has to be taken in terms of context, and what I'll give you today are tools that I think are going to push you in the right direction. And then when you evaluate those models, it should, you know, improve the adverse impact ratio, for example. Okay, so just a little bit about like, where does all this new stuff come from? It comes from information theory. So the foundation of Admissible ML is based on information theoretic principles and non-parametric methods. So, and then there's a concept called conditional mutual information, or CMI, and that captures multivariate nonlinear conditional dependence between the variables non-parametrically. That's a lot of words, but they're all there for a reason and they're meaningful. But I will try to explain this a little bit. So the setup is basically you have your X, which is just your, your training set, your predictors. Then you have the response, which is the thing you're trying to predict. And then in some cases, you may have what we'll call S, or the sensitive variables. And so one thing to note about conditional mutual information is that the CMI of y comma x given x is 0 if and only if y is independent from x given s. So again, I'm just saying this for people who like math and who want to see what this means in terms of like equations. And right below that is sort of a graphical model about how things can work. So you have x, that's like your typically like safe variables. Let's say it's like, some payment variables, and you're trying to figure out if you should give this person credit. So things that you wouldn't think would be dangerous. S is your sensitive variable. So, age, gender, race, etc. And Y is the response. So sometimes the pathway between X and Y is actually through the sensitive variables. And that's what we're trying to detect. And we're trying to detect the ones that the variables in X that affect Y, but through S, if you think about a graphical model. All right, so hopefully I'm not going to hurt anybody's brain right now. These are what I would say, I'm just sort of pointing you to a few equations from the paper. So if you do want to read the paper, these are the kind of main ones to look at. So this is a theorem that basically, tells you how to compute the mutual information, and then it's sort of giving you an estimator about how to do that in an unparametric way. And let's see, CMI measures how much information is shared, not only between X and Y, that is not contained in S. Okay, so I'm really going to kind of go quickly on this because I don't think it's super helpful unless you want to go read the paper afterwards. But this is basically what the algorithm is. The way that we calculate this stuff is that we use machine learning to do estimation. So you can use any kind of estimator. So internally, we're actually using any kind of supervised machine learning method. We use GBM by default, but you can switch that in the software. It doesn't really matter. It's just used to estimate something. And then you're able to extract these conditional probability estimates. And then you're able to get these mutual information values. So just basically very high level. And so now I'm going to kind of move beyond this a little bit and just kind of introduce just one more term that we use called net predictive information. It's just kind of a rewording of CMI. So it's sort of just an interpretation of what CMI is used for in this context. So really it's measuring and all of this will make sense in a minute, I think, when you see the infogram, because we'll put it into a more practical perspective. So, all right. Actually, I'm just going to skip to that because I think we're ready. Okay, so what is this infogram? So we actually have two types of infogram. So infogram is just this plot that you see here. It's a visual tool, much like a partial dependence plot. It's a visual tool that helps us understand our data. And there's two types. There's one that we call the core infogram and one that we call the fair infogram. And the fair infogram is for when you have demographic variables or protected variables in your data. Not every data set has that. You can still generate an infogram and learn about how variables have unique information and how they relate to the outcome. So that's what we would call the core infogram. So this is just the iris data set. So I am hoping that this will make more sense as we see it a couple more times. So on the on the infogram, the x-axis for the core infogram is the total information. So we're talking about information theory here, but really what this is you can think of this as like variable importance. This is just how predictive is each variable in predicting the outcome. So on the right, it's very predictive, highly predictive of the outcome. On the left, not so predictive. So what we see here is in the IRIS data set, there's two variables that are in our admissible section. The upper right hand is what we call admissible. The L-shaped thing is what we call the L features or the inadmissible features. So the goal here is really to just get rid of the L features, and you're just left with these like pure, wonderful features that have sort of unique information in them. They're not redundant, and they're highly predictive of the outcome. So in this case, we have two variables that have almost no predictive power because they're having zero total information. Remember, that's sort of like zero variable importance. And then net information is the y-axis, and that is like how much new information is there. So is there anything beyond like what petal width is already telling you, or petal length? You know, the one in the lower left-hand corner has very little net or total information. The one on the, you know, midway up the L, that one has some unique information, but it's actually not very relevant to the outcome. So also not very useful. Okay, so I mentioned that's the admissible section. This is the inadmissible features, just to point that out more clearly. All right, so let's talk about the FAIR infogram, because this talk I'm going to focus a lot more on the fairness aspect. So we have the same thing, the same diagram. We're going to use different names to refer to the X and Y axis, but underneath it's really the same thing. On the X axis, it's like variable importance, and on the Y axis, it's conditional mutual information, which in this case, we're going to call the safety index. So the more safe a variable is, means like the more it's just, if you think about the graphical model again, the more it's just going right to the outcome and predicting the outcome, not through the sensitive variables. And the ones that are sort of at the bottom of the safety index, basically how these variables work is they're sort of like a secret pathway through the sensitive variables, injecting bias into your model. And so that's why if you train a model using all these unsafe variables, you're still going to get bias at the end if you measure with AIR or other things. And you're gonna be like, why is this here? I got rid of all the demographic data. How is it getting in there? It's getting in through the secret pathway, sort of a back door. So the goal here is to basically get rid of all these unsafe or irrelevant variables. This is a credit data set. I think I have an example of this later. So again, same thing, but we're gonna just sort of focus on the FAIR infogram because I think there's really a good use case for it, and it's safety with machine learning. Okay, so how do we, yeah, does somebody have a question?
Yes, Colin asks, can you say anything about how total information is related to other measures of features importance? The Shapley value.
Well, it's similar to like things like the Shapley value, but it is actually just variable importance. So we in H2O and in most machine learning platforms, you can calculate variable importance. It's literally that value. So we ask H2O, what is the variable importance for each of these variables? It's probably something that we could have just called variable importance. I'm sort of replicating the terminology that was used in the paper so that it's consistent. And but yeah, it's literally just variable importance. So that's what you can think about it as. And variable importance is also, you know, it's a global model metric, whereas SHAP can be per row. You can also aggregate all the SHAP values over the whole data set to get sort of like a global level variable importance, but that would be like the main difference.
We also have one question from the audience here.
Sure.
It's not working.
Was there a question?
I'm sorry. So hi, Erin.
Hi.
So I have a question that maybe it's on the paper also. So how your base model is identifying the basically the variables those have demographic or other kind of biases, and how is it able to find the derived variables? There might be like, I understand that there might be some basic identifiers through which we are identifying bias variables, but how is it able to even find some other complex derived variables?
Okay, so yeah, first I'll just say, you know, the user would say, here's the protected variables, and it would have, the user would have to say the race column, the age column, whatever. So once we have that information, then it's using all this conditional mutual information calculations to calculate what basically for each variable, it's calculating like how much, let's go to the fair one. It basically just uses a bunch of math, let's just call it, to calculate like how safe is it. And safe is defined as like the conditional mutual information. And really, if I go back to this one, maybe, basically what we're suggesting is that if the information content in a variable, let's say it's just some payment variable that you don't think has anything to do with gender or race or whatnot, if we find that there's not very much exclusive information that's in that variable, that's not sort of mediated or going through the sensitive variables, then it will have a low safety score. And that's kind of what we're graphing on the y-axis. And it's really, yeah, it's different than if you just say, let me take like the correlation between the payment variable and the outcome. It's a different way of finding how it's sort of, I don't want to use the word correlated because it's not exactly that, but it's just a different way of looking at how information passes through a system in a learning system. And hopefully, I don't know if I can fully answer the question without going too deep into the paper. So I would say, yeah, take a look at the paper and you can read more about it. Okay, so just moving on. So how do we do this in code? So if you are not familiar with H2O, it's a library that is a lot like scikit-learn in Python or tidy models in R, caret in R. It's a tool that has a bunch of machine learning algorithms in it with a common interface, and everything kind of is in its own ecosystem. We have all the, you know, cross-validation, grid search, like model metrics, visualizations, the whole package together in H2O, and you can use it from R or Python. So everything that we do is in both. So this is how I would say, train the infogram. I don't know if that's the right word that I want to use yet, but basically we have a function called H2O.Infogram. Well, that's what it's called in R. And we give it the data, and this is the typical interface in H2O where we have training frame equals train. X is actually just a list of the predictor variable names or column indexes. And then Y would be the column name or index for the response. So we do kind of train the infogram because there is machine learning and learning happening inside of there. And it does train pretty quickly because H2O is quite fast in terms of speed. And then once we have this object, then we can plot it. And the object also has other information in it, which I'll show you as well. But the main way that you might want to look at it, at least first, is just plotting it. So here's basically the full amount of code for that you would use to do the UCI credit data set. So this is a data set from the UCI machine learning repository. The goal here, I think, is to decide like who's credit worthy, and it's based on some demographic data and also payment data, like your historical payment, like are you paying your bills on time, like how much are your bills, etc. So all of these examples that I'm going to show in the slide deck are from this link down here. So that's the user guide for Admissible ML. So you don't have to remember any of this. These are literally just screenshots from that page. So, you load some data in, you might want to split into train and test so we can actually evaluate this stuff later. And then you would identify, in this case, like what are the protected columns? So in this case, sex, marriage, and age. And then you train the infogram and then you plot it. And then another thing that you might want to look at is something called the admissible score frame. So that's just all basically the XY information for all the data points so that you can have access to the data rather than just seeing it on a plot. And so that's what this plot is that we saw before. So this is the UCI credit example. And basically the red dotted line you see there, that is a threshold that we have set. And you can change that threshold if you like. This is kind of what we've decided makes sense as a default, but you basically, it is a tool. So like, I don't want people to say the infogram said that these are fair and these are not fair. Like you have control over where that line is and how much you want to allow, like how safe do you need your variables to be, or how relevant do they need to be? Because you don't have to just take these two variables and then train a model on just those. You could decide to maybe include some that are sort of near the border, or you could iterate through and see, you can really evaluate, like as you add in more of the variables, like how quickly does the model become unsafe? And you could evaluate that based on different fairness metrics. So you don't have to do it this way. This is just the default.
We do have another question from the audience.
Sure.
Hey, so would you mind going back to your previous slide for a second?
Yeah.
When you're calling that ig.train function, are you training basically a bunch of different models, or are you just running it through those information equations?
We're just training one model. Well, we're using cross-validation. So technically, like by default, there would be five-fold cross-validation, but we're just training one model. And there is like an algorithm parameter where you can switch out what it is. But basically what that is, you can think about a machine learning algorithm as really just something to estimate things. And that's how we're using it. So we train basically one model within that, and that's used to like make estimates which are used in the conditional mutual information calculations. So there is training going on there, but it's not training in like the you don't get the model back to then make predictions later. It's just used to kind of estimate these numbers that we need.
Okay, thank you.
Mm-hmm. Okay, and so this is the other thing that you might want to look at is the admissible score frame. So this is just a list of all the variables that you had in your data set. And based on the default thresholds that we've set for sort of relevance and safety in this case, it will decide which ones are admissible. So if it's in the top right corner, they're admissible. So in the admissible column, you see one for the two variables there, and everything else is not. Admissible index is just sort of the distance between the top right point of the infogram and where the data point is. We don't really use that for anything. It's just kind of there because we needed to sort by that, or we needed to sort by something that made sense. So we just left it in. It might be useful for other reasons. But then you have The relevance index, which remember is just kind of like the variable importance, it's sort of a normalized variable importance measure, and then the safety index also normalized. And then the CMI raw, that is the same, that's the value that we turn into the safety index. So that's just the raw value, and then we normalize it to 1 so that it's easier to make sense. And that's why we call it safety index. But basically always on the y-axis, whether you have a core or fair infogram, is basically just conditional mutual information. And that's what you can think about. So if you, for whatever reason, want those raw numbers, we already had them calculated, so we put them there.
Hi, Erin, we do have a question in the Q&A.
Mhm. Sure. Oh, I can't see the Q&A, by the way, because I don't have.
He asked, read the fairness index. Does it have natural units? He's trying to understand.
Oh, no. So both of the indexes, or all 3 of the indexes, well, yeah, the relevance and safety indexes are just sort of normalized versions of other things. So the units are gone because they're normalized to 0, 1. So there aren't really units on that. CMI raw, I think, I'm trying to think of like what scale it's on. I have to think about that more. I look at the paper. But yeah, you really, this is all sort of relative and relative to your data. Okay, so then we're gonna talk about a real data set, which I like a lot. This is called the HMDA data set.
Hi, Erin.
Yeah.
We do have another question from the
Oh,
audience.
sure.
Hi, Erin. So I have a question. So in order to use this model, is the user needs to know about the protected variable?
The user needs to tell us which ones are protected. So you would have to think like, okay, I have something called age, and like you have to decide on your own whether you want to protect those or not. Because of course, like if you're in one country, some things might be protected legally. If you're in another one, it might be different. So we don't want to like infer anything about what needs to be protected, but I will on the next slide provide you at least a list of the protected attributes for lending in the US. So I'll give you like the full list. So yeah. So yeah.
Okay.
Sorry.
Sorry. So my question is that this model, that maybe if I can think about it as a like pipeline, would the selected feature set might be going to your AutoML model, or is AutoML that the unit is including now that this admissible variables automatically? How would it look like in order to build a fair model?
Yeah, good question. So where we're at right now in terms of our development is that we have the H2O.Infogram function, and you can really just think about that as a feature selection method. So if you do use it within some kind of pipeline, like let's say you replace whatever existing feature selection method you have with this one, you want to think about the validation strategy and all of that like you would in a normal situation where you're doing feature selection. But at this point, we have it as like separate things. So you do the infogram, you get the admissible features, and then separately then you go on to train models or AutoML or whatnot. And I'll show you that in a minute. So you'll see the workflow.
Samantha asked whether you were going to be sharing the slides of this.
Oh, yes, I will. I have them. I meant to put them in a tweet, but I haven't done that yet. But I will share them directly, and I'll probably put them on Twitter as well, a link to it.
Thank you.
Mm-hmm. Okay, so just a quick example. So this data set, the HMDA data set, is, well, it's based on this law. So there's a law that says certain institutions, generally like lenders, banks, need to maintain, report, and publicly disclose loan level info about mortgages. So what that means is like for each loan that they give, they need to document that and they need to publicly disclose it. Of course, they remove like the personally identifiable information, but it does have these important features like sex, age, ethnicity, and race. So this is a very useful data set because it is a bit hard to find data sets that have this information, especially like real data sets used in the world that are important. So I highly recommend like using this as a way to sort of debug your fairness endeavors and always it's kind of just a good data set in my opinion. So the goal here, it's a binary classification problem, and it's basically a data set that shows like which applicants get a high priced loan versus like a regular priced one. And there's a definition of what high priced means. I think it's, I have it listed in the documentation for Admissible ML, or it's on the website. But essentially it's just some metric where it's like, if it's X number of % higher, then it's called a high price loan. And, you know, it basically costs more money to borrow that money for your house. So it's a big deal, you know, if your mortgage payment is whatever, or if it's $500 more a month just to borrow the same money, it's a big deal, and it can have a huge impact on your finances. So just a introduction to like some more law stuff. So there's actually several different laws that protect consumers from credit discrimination. So there's one called the Equal Credit Opportunity Act, and there's also the Fair Housing Act, specifically for home lending. So it's basically illegal to refuse you credit if you qualify for it, discourage you from applying for credit, or give you credit on terms that are less favorable, like a higher interest rate, to someone else with similar qualifications. And so you can't give somebody who is basically the same person, but the color of their skin is different, 2 different rates, or their religion is different, or their age is different. Like that's just basically illegal. So, which is good, because yeah, before we had these laws, it was just, I mean, there's still lots of discrimination. I'm not going to get into all the other ways that happens, but this is a good thing that we have this law in the US. You can read more about it at that link. Okay, so then, yeah.
You have another question.
Mhm.
If you have 2 variables and one is drawn from the other, and you have outcomes, is that sufficient to use this ML model?
If you have 2 variables, like
The example given is you have gene mutations they're on, and then the outcome is disease severity. Will this work in prediction?
Yeah, it should work. Like if you said one of the genes was like, you know, well, I guess I don't know if this is like a fairness example or the core example, but in both cases, if they're sort of derivatives of each other and one of them you know about is like, you know, needing to be protected, then the other one should be identified through this process. There is an example about using like a genomic data set in the paper, which I think is a cool example, because in that particular case, it wasn't about fairness. It was just about, could we, you know, often in these genomic data sets, there might be like 30,000 columns of like different genes, and you don't know which ones are useful or important. So you might try to do some feature selection. And in this particular example in the paper, we're able to basically take a huge data set and reduce it to 2 genes. And then you can train a decision tree, an interpretable model on those 2 genes. And then you get this tiny little model that's fully understandable to a human. And actually the accuracy is not that bad compared to like if you just put the whole thing into a random forest or something. So check out that example. The paper that I'm referring to is the Admissible ML paper. And I had a link to it at the beginning, and you can find it on arXiv, but yeah, you'll get the slides and there'll be a link to it there, or you can just search Admissible Machine Learning on arXiv. Okay, so this is how you just, this is the HMDA example. I mean, we've already seen the code a couple times, so we kind of know how this works, but you can see what the columns are. So we've got like, in terms of our, the variables that we don't think should be bad are loan amount, loan to value ratio, loan term, intro rate period, property value, income, and debt to income ratio. So we think, okay, these are all just sort of numbers about people. They're not encoding gender, race, or sex, but in fact, that's not what happens. And you can see the protected columns here is ethnicity, race, sex, and then two different versions of age, the age itself, and then a binary indicator if they're over 62. So this is what the infogram looks like for this. And so what we had 7 features, I think, to start with, and then we end up with 3 that we think are acceptable to put in a model. So what that means is this loan amount, property value, and loan to value ratio are really only the good ones in the group. And so the ones, if we look back to that are bad, so income, that's actually not a surprise. That's usually something that's correlated with demographics. And then like loan, I guess, let's see. Yeah, loan term is also in kind of the bad area. So it might be that certain demographics apply for different length loans, like a shorter loan or a longer loan. And so somehow that's encoding other biases that are sneaking in there. This is what the admissible score frame looks like. So you can see the actual values of everything. And yeah, so then what would we do with this information? So now that we have what we're calling the admissible columns or the admissible features, we can, as an experiment, train like a GBM, for example. It could be any model, a random forest, like GLM, whatever. If you want interpretability, you would want to maybe train a GLM or a decision tree. But let's just say we're wanting to train a GLM. So we could try like 2 things. We could try with just the admissible features and see how we do. And then we could do it with all the features that we know kind of are probably sneaking in some biases. And so right here, I guess the point of this exercise is to show that you really don't lose a huge amount of performance by being safe. And at least in this particular example. So, we've trained 2 models here, and one of them is just is the admissible, what I would call the admissible GBM, and we've got an AUC on the test set of 0.814. And if we just put everything in and we're just only concerned about maximizing performance and we didn't care about being fair, we would get like an 834. So there is a penalty, because those variables do have information in them that are predicting the outcome. It's just not the information that we want. Doesn't mean it's not there. Doesn't mean there's not, I mean, if it, I guess if it wasn't, well, okay, I'm just going to stop there. But basically, what I'm trying to show you here is there's just it's not a huge deal. You can maybe sacrifice a little bit of performance to get a safer model. And I won't say that you could always, there's always trade-offs in machine learning. So there's also trade-offs in terms of like model complexity. You can train like a very massively complex, like 20 layer stacked ensemble and get better performance, but then it might be really slow to generate predictions. So we're always used to dealing with trade-offs in machine learning. And so I think like, I'd like to encourage people to sort of move out of like a singular metric type of way of evaluating machine learning models, and then sort of broaden the horizon of like, okay, we're going to look at model accuracy, we're going to look at fairness, we're going to look at prediction speed and production, like things like that. All of these things are just pieces of information that you might want to use to choose a model. And what I don't have currently in the user guide or right here is like the code to then calculate all of the fairness metrics on these models. That probably will be something that I will add in like soon or after this, but this is what we have right now. So you can just see, there are links in my user keynote talk that I mentioned that will show you how to do that. But let me just sort of add one more thing. So admissible AutoML, I'm going to just sort of introduce what this means. So with AutoML, usually your goal is kind of to get sort of the best model that you can within like a certain fixed budget, let's say. So one thing to note about when you're doing admissible machine learning is, really what this is it's a feature selection method. And so when you have fewer features, the data is smaller and you're going to be able to train your models faster. So one thing is that you're getting faster models. So within a fixed budget, you're going to be able to cover more of the search space. So that's just something to note. It might, again, not necessarily give you higher performing models, because remember, we are removing information. We're hiding that information from the model by removing the inadmissible features. But one thing that is nice is that, for the same price, let's say, we can train more models because we're able to do it faster. So, so kind of like the goal of all this is to really make this all automated so that it's not hard. And, we give you visualizations where you can kind of learn about your data, even if depending on whether you want to train models with it afterwards or not, you probably do, but it's kind of a separate thing. So this is just, and I keep using the mask emoji, number one, because I believe in wearing masks and I like respirators, but because I feel like it's kind of like this, safety thing where we're really putting some kind of filter on the machine learning that we're doing, and we're really just like allowing, it's just a more safe way to be. So kind of trying to emphasize like, safety and personal responsibility and all of these things these lessons that we've been challenged by during the pandemic. Like, let's, learn something from this and try to be more safe. Okay, so then this would be just the equivalent of, it's basically the same thing as what I did with the GBM, but instead of training just a single GBM, I'm training a whole AutoML run, which will train as many models as you like. In this case, I'm asking it to train for 10 minutes, which is in practice not that long. You might want to run it for longer, but if we ran it just for 10 minutes, like here's like the two versions of what you would get. So we have an admissible AutoML getting like a 0.826 AUC on the test set. And then like what I would call the unprotected AutoML gets a 0.85. So, it is better. It is better in terms of just accuracy, but you are not, doing something discriminatory or potentially illegal. So that's, I guess, the value. But what I will point out is if you look at the admissible AutoML score of 0.826, that's still higher than, 0.826. Oh, it's not. I was going to make a point that you could use AutoML to get higher than like a single inadmissible GBM. But in this particular case, they are quite competitive, 0.834 versus 0.826. So that's basically at a high level and like what this new concept is of admissible machine learning and the Infogram. These are some links that you might want. So the main one is the Admissible ML documentation. So it's very similar to like what I've presented today. And like I said, like in the near future, this is just like really just released last month. So it's brand new, and we'll be trying to like extend some of the fairness metric stuff. So one of the reasons that well, I wouldn't say like the reason, but one of the things that I'll mention is there's another metric in the paper that we have not implemented yet. So it's called alpha testing. So this is something that we'll probably add, and it's sort of a different, let's just call it a different fairness metric. It's a little bit more statistically principled, I would say, than using something like adverse impact ratio or something like that. So it's just another way of sort of, once we have the models, how do we test? Is there like a test for like, again, I really discourage from like framing it like, is it fair or not? But you're having a testing tool that's sort of helping you to answer how fair it is. And so that's something called alpha testing. It's one of the things from the paper that we haven't had time to implement yet, but that's probably what we'll do next. And so then you'll have more tools to sort of, certify, let's say, that your the models that you've trained that are called admissible are actually measurably more fair than the unadmissible ones. So yeah, that's what's coming next. And yeah, that's the talk. And I know we have a couple minutes left for questions, so feel free to ask me more questions.
We have a couple of questions. We have one online. Hardik asks, does the Infogram technique work for a time-varying data set, or are transformations required to correct for things like seasonality?
That's a good question. Let me think. I know that we haven't, I think like it depends on the type. I think if you used, so I would say there's kind of like two types of, well, there's probably multiple types of like time series type of data with machine learning. So there's something that I would call the pooled repeated measures type of data set. So this is a term like from biostatistics where I come from. So what that's kind of a time series data set. So the idea is that you have, let's say in this case, multiple time points from each patient in a data set. Let's say you're doing some kind of longitudinal study and you do, periodic check-ins of their labs or other metrics that you're measuring about patients. That type of time series data set, like as long as you put each patient or cluster or user or whatever the concept is, but just think about it as cluster. It's as long as you do, if you're doing like cross-validation, you make sure all the rows from one patient go into the same fold. You can still do like normal machine learning. Like, however, if you have like a really just kind of like not IID data, but data where just there's some sort of strong distribution shift and things are shifting over time, then most machine learning algorithms aren't set up that way. So I guess it would depend specifically like what type of time series you have. Like, can you abstract the time element by taking, like, if there's a date column, could you just turn that into like day of the week or month or something like that? Then sure, you could do this. But if it's something more complex, then I'm not sure about it.
Well, let's take our final question from our audience.
Hi. So before I move on to my main question, I just want to check if my understanding is correct. So could you go back to the infogram slide?
Do you want to see the fair infogram like this?
So am I correct to say that like a sensitive feature would basically I in the bottom right of it? Like the bottom right of the L.
What were you asking? If there's, what about those ones?
The feature
Yeah, so those,
very relevant, but very unsafe.
no, the ones in the bottom left in this particular example, those are both not relevant and unsafe. So you might, if you had something that's like highly relevant but unsafe, then it would be on the bottom right of the L.
That's what I'm saying. So
Yeah.
like a sensitive feature would most likely be at the bottom right. Correct.
If it was what kind of feature?
Sensitive feature.
I didn't hear the word that you said. That it's something
Sensitive feature.
sensitive. I see. So if it was a sensitive, yeah, I mean, if it was so I guess you can't really calculate a safety index for a sensitive feature because you're conditioning on those features to begin with. I guess it would be highly unsafe. It would be like 0 since we're defining it as such. I'm not sure if I'm really answering your question, but
Yeah, getting there. So like, and then suppose we have like a non-sensitive feature that is highly correlated with the sensitive feature, then it would also be at the bottom right.
yeah, so if it was like something like zip code, for example, highly correlated with race, that would be in that would be on the safety index towards 0, and then potentially on the relevance index it could be high. Like that might be highly predictive of whatever it is that you're trying to predict, but it could be even all the way over to 1, but it would be very low on the safety index.
Okay. Then would there be cases where we have like a non-sensitive feature that is actually not causally related to a sensitive feature, but it just so happens that they are very highly correlated?
I think there's some simulated data in the examples in the paper that cover this particular case. I can't remember, I have to revisit, but I think it basically does detect that. I don't know if it's, yeah, I guess if it's not like really, like if the graphical model, if they were fully independent, then it might not show up. I actually can't remember. I'll have to look at that. But I do think there is an example in the paper that sort of probes this question of like, what if it's highly correlated, but somehow not passing through the sensitive variable? Yeah, I have to look at that. But you might find the answer in the paper.
Well, thank you so much, Erin. I think we're out of time. So just one last round of applause, please. Everyone for attending, everyone attending. See you somewhere else. You just
Yeah, I'll probably get rejected.
Okay. Like 2:30 or 2:20.